From the RSNA, I'm Dr. Jana Ivanidze, and this is the Radiology Imaging Cancer Podcast. One of the reasons I went into radiology, and I'll go out on a limb and say that this is probably true for a significant number of my colleagues, is that I love science fiction, and I always felt that our specialty is at the forefront of technological advancement in medicine and life sciences, bridging science fiction and reality. So I'm especially excited for today's episode since we are going to talk about emerging technologies which are not yet in clinical practice but hold promise to positively affect oncologic imaging and therapy in the not-too-distant future. We are first going to hear from Meredith Jones and Dr. Lacey McNally, the respective co-first and co-senior author on an article recently published in Radiology Imaging Cancer focused on multispectral optoacoustic tomography, or MSOT. Dr. McNally is an accomplished researcher at the University of Oklahoma with a focus on novel approaches to cancer imaging and therapy. Meredith Jones is a PhD student in Dr. McNally's lab. Dr. McNally is also the deputy editor of Radiology Imaging Cancer, and Meredith is a trainee editorial board member. Dr. Matt Seager, interventional radiology resident at King's College Hospital in London, who is also on our trainee editorial board, will be conducting the interview. We will also hear about a very different, but no less exciting and science fiction evoking approach to cancer imaging from Dr. Guillem Pratx, whom I had the pleasure of interviewing. Dr. Pratx is an assistant professor of radiation oncology and medical physics at Stanford University, and he will be talking to us about his fascinating work centered around single-cell PET.
Hello everyone, my name is Matt Seager. I'm a final year interventional radiology trainee working at King's College Hospital in London, and I'm a trainee editorial board member for Radiology Imaging Cancer. As part of this episode's focus on emerging imaging technologies, I have the pleasure of interviewing Dr. Meredith Jones and Dr. Lacey McNally on their paper recently published in Radiology Imaging Cancer, which is entitled Development of Multispectral Optoacoustic Tomography as a Clinically Translatable Modality for Cancer Imaging. Both Meredith and Dr. McNally serve on the editorial board of Radiology Imaging Cancer, Meredith as a fellow trainee member and Dr. McNally as deputy editor. Meredith is a second-year PhD student in the biomedical engineering department at the University of Oklahoma. She received her bachelor's degree in physics in May 2019 from Muhlenberg College. She is currently working under Dr. McNally on multispectral optoacoustic tomography. Dr. McNally is the program leader for cancer therapeutics at the Stevenson Cancer Center and an accomplished translational scientist working at the University of Oklahoma. She has extensive experience in clinical collaborations, grant writing and reviewing, and project development. She has mentored medical residents and fellows and multiple clinicians in research and NIH proposal writing. Her research focuses on novel cancer diagnostics and imaging technology with the goal of rapid translation to clinical care for patients with solid tumors. Welcome to you both, and thank you very much for joining us today. I read with great interest your paper on the emerging clinical applications of multispectral optoacoustic tomography, or MSOT, published in our journal this month. My first question is to really set the scene for the audience. Please, can you explain what MSOT is?
Yeah, so thank you so much for having us. We're super happy to be on this podcast. So multispectral optoacoustic tomography, or what we like to call MSOT, is a non-invasive, non-ionizing imaging modality that takes advantage of the photoacoustic effect in order to generate medical images. So nanosecond pulses of NIR light are going to be used to excite the tissue, and this excitation is going to cause a thermoelastic expansion and thus the production of acoustic waves. So these acoustic waves are then detected by an ultrasound transducer where they're then going to be reconstructed into images. So MSOT uses multiple wavelength illumination, and this allows for the simultaneous identification of multiple chromophores through the decomposition of the observed signal into its components based on their spectral shape. So this is what we like to call spectral mixing. So it's through the spectral mixing that we can identify where the signal oriented and the relative abundance of the signal at that location.
Awesome, thank you very much. And what are the potential advantages over other imaging modalities?
Yeah, so when I think of potential advantages, I think of the resolution. So biological tissue is highly transparent to NIR light. So the use of NIR light to illuminate the tissue, coupled with the generation of mechanical acoustic waves, makes photon scattering pretty much irrelevant to the image formation. So this allows for increased depth penetration with no loss of spatial resolution. So we're getting spatial resolutions around 75 microns for the preclinical instrument. And this makes MSOT super advantageous to many other modalities that must sacrifice spatial resolution for either depth or temporal resolution. So what comes to mind as an example is mapping of the vasculature. So since MSOT is able to resolve oxy and deoxyhemoglobin based on their spectral shapes, it's great for mapping vascular structure and function through surrogate biomarkers such as oxygen saturation and total hemoglobin. So this can be done using fold MRI or arterial spin labeling or ultrasound with microbubble contrast, but all of these modalities have a very limited spatial resolution where MSOT does not. So in addition, another advantage to MSOT is in its ability to resolve multiple spectrally distinct agents at the same time. So this allows us to exploit the molecular signatures of many diseases through the administration of NAR-sensitive contrast agents. So the absorbance spectra of this contrast agent can then be unmixed from the prominent background absorbers, whether that's oxy and deoxyhemoglobin, and then we can uncover information about the molecular target, which is telling us about the disease. And we can do this with a very high sensitivity and specificity, so preclinically. So all that being said, MSOT is going to be extremely helpful in terms of cancer, since MSOT will have the ability to distinguish tumor from healthy tissue based on differences in vascularity, perfusion, or molecular characteristics if we're using a targeted exogenous agent. These are all extremely difficult and almost not possible using traditional modalities such as PET, MRI, or CT.
Awesome. You've touched on a few areas there, but where do you see the most promising clinical applications for MSOT, and what are the potential barriers for its clinical implementation?
So this is Lacey McNally, and as far as clinical opportunities, MSOT is a newly emerging technology. It's a version of optoacoustics that uses a multi-wavelength laser that allows for the identification of multiple chromophores. Other optoacoustic imaging machines sometimes have only had 2 lasers, so that limits you to maybe more. Limits you to maybe just hemoglobin or a single chromophore, but the multispectral nature of MSOT allows for the development of new exogenous agents. And I think that's where it really can shine in the clinic, because current use of let's say more traditional modalities, CT, MRI, or PET, or ultrasound, you really only can see a very few number of things. So maybe you can see just blood flow, maybe you can see just soft tissue contrast. Maybe you can just see a particular nanoparticle. But MSOT can allow for multiple agents. And as long as the spectrum of those agents is sufficiently different enough amongst each other, then that allows and facilitates separation. In our own laboratory so far, we have been able to distinguish up to 5 different agents at the same time. And you can imagine that in the clinic would allow for a lot of opportunity, particularly with looking at molecular signatures of certain tumors. Maybe you have a tumor that is a HER2 positive breast tumor. It could theoretically be possible for you to distinguish how much HER2 receptor was there in a particular location. At the same time, you could look at oxy and deoxyhemoglobin. So that could allow you to see a lot of characteristics of that particular tumor. Same is true for EGFR in head and neck cancer, right? So I think the ability to use this as a companion diagnostic, particularly in the context of targeted therapy, is a real niche for this type of imaging. There are, of course, others, but I think that's something where it truly can shine.
And what would be the potential barriers for implementing this technology in the clinical setting?
So the different barriers. So first, there's regulatory. We can't take out regulatory. That's probably, in my opinion, the biggest barrier because at the moment, MSOT does not have either FDA approval or CE approval, although they're working on it in both cases, but it's not available as yet. So I think clearly regulatory levels are the very first. Also, a barrier would be actually having a device. Of course, that's important. If you don't have a device, you can't do the type of imaging. And as it's newly emerging, those are not frequent around the world. They are increasing, but not in every hospital. So I think as with any type of new imaging modality, you have to kind of see how it plays out and what kind of clinical applications really turn out. And then, of course, just how many have them. Probably it's going to be in tertiary cancer centers. That's my guess. Probably it's not something at your local, hospital, but I think it's certainly something that can happen in larger hospitals.
Moving on to another sort of area in terms of mentorship. Meredith, you've worked on this article with your mentor, Dr. McNally. How important is mentorship in your career development as an imaging scientist?
Yeah, so I think having a good relationship with your mentor is extremely important for career development. So this is for many reasons, and the first would have to be skill development. So it's imperative to have a good relationship so that you can be comfortable having those constructive conversations and getting meaningful feedback on your work, whether this is grant writing, manuscript writing, or just developing laboratory skills. And for example, MSOT is super up and coming, so the literature is not very extensive. So Dr. McNally's guidance is always extremely beneficial and often points me in new directions, which ultimately help me to improve my skill set. And in addition to this, she's really helping to expand my network through introduction to collaborators and new career opportunities, whether these opportunities are conferences, poster presentations, and then it's through the exploitation of these new opportunities that I can better understand where my passions in imaging lie, so that I can continue in this direction once I complete my PhD.
Fantastic. And regarding the trainee editorial board, Dr. McNally, as a senior editor, why did you and the rest of the editorial board feel it was important to involve trainees? And to Meredith, what has the experience been for you in working on the trainee editorial board?
So the Gary and I and Bonnie Jo and Luke also had really discussed and Ashok also have discussed an opportunity to expand our horizons as a new journal. And not only that, but I think it allows, the idea was to allow junior members the opportunity to see how papers come about. That's one of the true learning opportunities. It's very hard for especially new investigators to look at their own work objectively, because everybody, even the senior mentors, think that their paper that they're submitting is the absolute best thing that they could possibly write, or else they wouldn't have been submitting it, right? And so it allows for, the idea is to allow for trainees to learn to critically read manuscripts, to critically review manuscripts, to be able to interact with senior members and to see, why did somebody choose, why did somebody comment in a paper in a particular way? How do you delicately say, oh, you need controls for this? How do you, why do you need controls? How to look at controls, how to look at statistics, how to look at areas that are related to the area that you're working in, but maybe not exactly the same area. And so, how to apply different imaging modalities to different disease types. What might work in one thing may not work in the other. And so it was really an opportunity to give several junior members an opportunity to interact and to facilitate their own career development, particularly in getting their feet wet for reviewing.
Thank you. Meredith?
Yeah, so being a member of the editorial board has been an extremely positive experience so far. Getting the opportunity to review manuscripts and listening to extremely well-established doctors and researchers discuss these manuscripts is really helping me to think critically about the manuscripts that I'm reading, as well as plan out my own experiments. This is in terms of, better controls, better ways to articulate to my readers my results and where I think that this is going in the future. So I am extremely grateful for the opportunity to be sitting on this editorial board.
Yeah, I'd completely echo those thoughts, really. I think you learn about reviewing papers, but moving on from that, taking it a step forward, you anticipate what journals and experienced researchers are going to say about your own work. So I think it really does help develop, your own skills in designing projects and writing them up and carrying out research. So I'd really encourage anyone who has an opportunity to get involved with an editorial board as a trainee to take up that opportunity, because it really is a very positive one. Guys, thank you so much for taking time out of your busy schedules to join us and to talk about your fascinating MSOT paper. It's been a real pleasure to talk to you both, so thank you.
Thank you so much for having us.
Cheers.
PET imaging is a critical component of clinical management of patients with cancer, as well as the focal point of numerous clinical and translational research projects focused on improving cancer detection and treatment response assessment. Dr. Guillem Pratx has developed a fascinating approach allowing the tracking of single cells using PET, using a combination of computational modeling of cell trajectory and radionuclide delivery into cells using nanoparticles. His group's work was published in, or most recent work, among many, many other publications, was published in Nature Bioengineering earlier this year. The manuscript is entitled Whole Body Tracking of Single Cells via Positron Emission Tomography, with Dr. Pratx is senior author and Dr. Zhang is first author, and we will post a link to our podcast page. So we're very excited to have Dr. Pratx with us today. Brief overview of his very impressive career. He studied engineering at the École Centrale in Paris and subsequently completed his master's, PhD, and a postdoc at Stanford, where he subsequently has been leading the physical oncology laboratory for the last 7 years. He has received numerous awards for his pioneering work, among them the Society of Nuclear Medicine Young Investigator Award, the Damon Runyon Ratcliffe Innovator Award, and many others. And his group works on the development of instruments and algorithms at the interface between medical physics and cancer research. And so we're very excited to have Dr. Pratx with us today to talk about his pioneering work on single-cell PET. Welcome.
Well, thank you, Dr. Ivanidze, for the kind introduction, and especially for the invitation to share my research with your listeners.
Thank you. So can you tell us a little bit more about your career trajectory and how you became interested in PET imaging?
Sure, yeah. So growing up, it's funny because I was very interested in math and engineering and had almost zero interest in medicine. And my parents always used to joke that it was very likely I would ever be involved in medicine because I was kind of terrified of blood and so on. And then I ended up at Stanford, where I did a PhD in electrical engineering. And during that time, I had the opportunity to work on a intraoperative gamma camera that was designed to help with sentinel lymph node biopsy in breast cancer patients.
Oh, wow.
And interestingly, I ended up doing almost 50 surgeries at Stanford, with the surgical team there, and that really, got me interested in imaging and medicine. And so I think after that, I ended up working on positron emission tomography, and I think as an engineer, I always found imaging very fascinating because what we're able to do nowadays, when you do an MR scan, we actually, measuring the spins of the atoms in the patients, and when we're doing a PET scan, we're using antimatter to localize tumors in vivo, right? So I mean, it's really advanced technologies being used to create those images, and it's I always found that very interesting.
I always like to say it's like science fiction, but that's our actual job. And,
exactly. Yeah, and I think a lot of it is inspired from science fiction. All the abilities we have today in medicine is truly outstanding.
Yes, very much so. So could you share with our listeners a bit more about the concept behind single cell PET?
Yeah, so this is a project that had been on my mind for a long time, and it really took at least 6 or 7 years to get to the point where today. And just for the listener, typically a PET scan is taken by injecting a radio tracer that will distribute in the body and accumulate in certain regions of the body. And after acquiring data, an image is reconstructed that shows where the tracer is. So it's really normally PET is used to generate images, which are really three-dimensional images, but they are images. And so with single cell tracking, it's a bit different because what we are trying to do is to track single cells. And so tracking is not necessarily the same as imaging. So tracking is more similar to, for example, using a GPS. So if you want to localize your cell phone, let's assume you lost your cell phone somewhere. and you want to know where it is, you can use GPS to find it and get a set of coordinates that tell you where the phone is, right?
Mm-hmm.
So it's sort of similar with single cells. What we do is we take single cell, we tag them with a radio tracer, and then we will inject them in vivo. And what we want to know is, what is the migration? How do they migrate? How fast they go? How do they go from point A to point B? And what are the kinetics? So really trying to understand the migration pattern. So these are not necessarily tasks that can be conducted using images. And so the cells is somewhere inside the subject, and we are getting data from the scanner. So these are gamma rays that are hitting the detectors. Mm-hmm. And then from the pattern of gamma rays that are detected, we are computing in 3D the coordinates of the cells from the PET data. So there's no images being constructed. It's really getting coordinates from the scanner. Mm-hmm. And so to achieve this purpose, we developed a new algorithm. That's something we published in 2014. So it's almost 6 years ago. But that's how long it took to really for the work to come to fruition. And based on the new algorithm, what we understood was that there's a certain amount of activity that needs to be inside the single cell for us to be able to track it dynamically using PET. Okay. Mm-hmm. And so typically a patient that receives a PET scan will be injected with about 500 millions of becquerels. So that's a measure of the amount of radioactivity that's being injected.
Yes.
And so for a single cell, what we are doing, we're not putting, of course, that much activity in the single cell, but we're putting 20 becquerel. And that's what we found is necessary for us to track a single cell. And roughly that's about 20 million times less than what's used for a clinical scan. And so that's a tiny, tiny amount. That's what I want to emphasize. But fortunately, PET is, I think today, probably the most sensitive imaging scanner available. For instance, so we're using preclinical scanners. They're smaller size scanners that are really designed to image mice and small animals. And these scanners, they can detect roughly 1 out of every 10 radioisotope decays. So if you have 10 atoms in the field of view, we can probably detect 1 of them. And so with a single cell, that's 20 becquerel. So that means 20 decays per second. Mm-hmm. That means that the scanner is getting about two events per second. And from those 2 events per second, we're computing a position in real time of the cell that's migrating through the body.
So in addition to the computational aspects of calculating the trajectory, this pioneering work also involved loading the cells with the radioactivity, and that also is very interesting.
Yeah, so that's a great point also. So the question, how do we load the cell with 20 becquerel of activity? And that's something actually took us, more time to figure out than the actual algorithm. Because although it's a very small amount of activity, the cells are really tiny, and so we have to find a way of getting the activity in there. Mm-hmm. And so for this, we ended up using nanotechnology, and not because nanotechnology is cool and exciting, but just because it has those unique properties. And especially, we selected a type of nanoparticle that was made from highly porous material. Mm-hmm. And we could use it as essentially a nano sponge to really soak up the radioactivity, so that then, instead of having a lot of radioactivity that's dispersed, we can focus all the radioactivity into a small number of nanoparticles and then efficiently transport those into the single cells. Just to give sort of a number, if we have 1 gram of this type of nanomaterial, the surface area corresponding to this would be about 100 square foot. So it's has very large surface area and allows us to get a lot of radioactivity into the cells. So
fascinating, really interesting. So, of course, as you mentioned already, this was all demonstrated on a preclinical micro-PET scanner. If myself being a radiologist and many of our listeners working clinically, where do you see challenges in translating this work to the patient?
Exactly. Yeah. So to do this clinically, we need a PET scanner that has very high sensitivity. And I think one may think that spatial resolution is really the criteria for whether a scanner can achieve this type of task or not. But actually, what's really important is sensitivity. So we have to be able to detect that very weak signal from the single cell. And I think, most PET scanners that I use in the clinic, they don't have very high sensitivity compared to the preclinical scanners because, first of all, they only image a very short section of the body, so maybe, tens of centimeters, and the patient measures, of course, up to, 2 meters. And that prevents you from getting all the gamma rays. But fortunately, there's actually work being done currently building those extra long PET scanners that can actually extend to cover the whole length of the patient, and these have much higher sensitivity. And so I think if we were to translate this to humans, we would have to use those newer scanners that have much greater sensitivity in detecting that tiny amount of radioactivity. But I would say it's not going to be easy. And the one of the reasons is that when we go down to such low level radioactivity, there are many unexpected things that happens. For example, the PET scanner is actually slightly radioactive, and that's something you don't expect. But when they build the detectors of the PET scanner, they have to mine certain metals that go into the scintillators. And these metals actually contain naturally a small amount of radioactivity. And so, we are really competing with sort of the intrinsic radioactivity when we try to detect the radioactivity of a single cell in the scanner. It's been a big challenge. And as the scanner gets bigger, there's more of that intrinsic radioactivity in the scanner. So I think that would be a challenge, but that's not something that, that's something that can be addressed, I believe. So.
Right. So you're talking about the LSO that's in the scanner. Yeah.
Right. Yeah. So this LSO is the material, and it's made of an element called lutetium. It's a very expensive material. And about 3% of the lutetium that's naturally occurring in the Earth is radioactive, with I think a half-life of several billion years. So it's a very long half-life. It's fairly stable, but if there's enough lutetium in a detector, gives rise to a background count rate of events. Something that people have noticed before, and we also came to notice during our work.
Right. Yeah. That's really interesting. So let's say we overcome these technical challenges and we, develop further the efforts you mentioned on the long axis, large field of view, a whole body dynamic PET scanner, where several groups are currently working on. What potential human applications of this technology are you most excited about? I was thinking that perhaps tracking CAR T cells could be one application, or possibly a screening tool for circulating metastatic cells in patients with known cancer. Are those some of the areas?
Yeah, I think these are great ideas. I think I would love to track CAR T cells because, getting the cells to the site where they're needed into the tumor is still, I think one of the biggest challenges for solid tumors. And I think the beautiful thing with single cell tracking is we don't need to track every CAR T cell that's injected into the patient. We could take a very small subset of them and say these are imaging reporters, because I think, and talking to clinicians sometimes, there's a reluctance to add an imaging reporter to the CAR T cell because it's already a very complicated process getting the cells and modifying them, and sometimes adding imaging can make it even more complex and even harder. But the idea is if we only modify a very small subset of cells, that this will not affect the therapy, but this will tell us whether the cells actually are going to the target and provide us the information we need, right? So one of the other things we've done is we really try to assess whether this labeling affects the health of the cells. And so that's something we really paid attention to. We generally find much effect of the radio labeling on the cells, but that's something we really have to pay attention to. And then the other interesting thing is there are multiple radio tracers that are available that have different half-lives. And so depending on whether we want to know the early stage of the migration, or if we're interested more in later time points, we can use different radio tracers. And you also mentioned tracking metastasis is something I've thought about. And I think it would be great, if we knew, so we know there are circulating tumor cells in the blood. It'd be great to know where they end up, right? Where do they really arrest? In which niches are they most likely to extravasate and give rise to metastasis? And I thought, if we could get those CTCs out, isolate them, label them, would that be okay to re-inject them and see where they go? And I don't know. I think the biggest question here is whether it's would be ethical to inject the patient with cancer cells, even though in that case, that would be the patient's own cancer cells. But I don't know. I mean, as a clinician, you probably wouldn't want to inject your patient with cancer cells, even though
that's a very good point. It would be a very interesting study to do in the animal, for sure.
It would be fine to do in animal. There's areas that those cells rest preferentially. Right. But clinically, yeah, I mean, I don't know. If we could label the cancer cells without taking them out, maybe that would be something we could do, right? And then that sort of remove that ethical question of reinjecting the cells.
Right.
But then potentially, looking at metastasis in vivo, I think is, still one of the greatest challenge we have in cancer is metastasis.
Absolutely. So that's really fascinating. So, I'm sure our audience would be interested to hear what are some active research projects you're currently working on.
Yeah, so we are continuing this work, and I think we're trying to make the process easier to perform, because right now, each experiment is a very significant undertaking. We're trying to kind of make things easier so that they can be run more routinely, make the labeling easier, and so on. One thing we're also trying to do is, so right now, when we do single cell labeling, we really mean tracking one cell at a time in an individual. And we would love to do is tracking multiple cells, but each cell individually moving at the same time. And so this is also a kind of a multiplexing problem. So trying to understand if we're getting signals from the scanner, how to disentangle the different signals to get information about single cells. So something we're working on.
These are cells labeled differently, or are they?
They would be labeled, in the same tracer and the same approach, but it's in terms of reconstruction, it's a little bit more complicated to localize multiple emitters, because the gamma rays, they don't have any different colors, or there's no way for us to know if a gamma ray is coming from cell number 1 or cell number 13, for example. Right. And so that would be it's more like a mathematical problem, I guess.
I see. Fascinating.
So that's we're trying to do that, and the idea is that perhaps we could track dozens of cells. So we're not talking about tracking thousands of cells, each cell individually, because that's certainly not doable. But at least tracking small population of cells is something we could do probably. And then I guess so I don't know. So this is the cell tracking. So we're also interested in other projects, and maybe I can briefly talk about it.
Sure.
Right now we have a lot of interest in looking at tumor organoids. So we're working with collaborators who are able to grow organoids from tumor-derived tissue in vitro in the lab. And these are really nice models of tumors, because they contains a rich microenvironment with all different cell types, the immune cells, the fibroblasts, and so on. They can be imaged really nicely. And so what we're trying to do is actually take PET scans of those organoids, really, really high resolution PET scans, trying to push the resolution down to maybe 20, 25 microns. And so how, now, like I told you, we had preclinical PET scanners, we can scan small animals. So now we're trying to see if we, trying to scan organoids and use them to either test new PET tracers or for, ongoing studies, and, use clinical PET tracers in those studies, so that we can really better relate what we see in vitro in those organoids to what we see in vivo in the clinic. So.
Really interesting, especially to, I'm sure, our listeners who, like myself, read those PET scans in the clinical setting to see what's possible in the future. So we'll be looking forward to more publications from your group, maybe in radiology imaging cancer someday. And thank you so much, Dr. Pratx, for joining us, and look forward to hearing more about your work again.
Well, thank you so much, Dr. Ivanidze. It was really a pleasure talking about my research, sharing it with your listeners. And I'll certainly be keeping in touch with the podcast, listening the other presenters.
Thank you. Thank you so much for listening. We would love your feedback, as always. Please subscribe on Apple Podcasts or wherever you're listening, and give us a rating to help more people discover our show. I'm Dr. Jana Ivanidze, and this is Radiology Imaging Cancer. Stay safe and see you soon.